So yes, I will talk about testing clock-based systems. So this is very industrial topic, and this is coming from use cases we have done with the SNCF, which is the National French Railway Operator, and Alstom, which is also a railway manufacturer. And out of these experiments, we came up with an approach, at least some thoughts that we would like to share with you. But first, let me explain what we mean by clock-based systems so that we are clear on what we are talking about. It's systems that have sensors, and they measure something from the environment, and they measure it regularly based on a clock. That's why they're called clock-based systems. Then the information is computed, and an output is generated every tick of the clock. So this is, as you can understand, a very low level, very close to the implementation. Still, there are two main clock-based systems. The first ones are logical systems. So the sensor is basically measuring 0 or 1. It's fairly simple. And usually with this type of systems, you have logical operators, you compute something, and you get an output. So you can have a lot of AND and OR gates. You can also loop the output back on the input and do some quite complex computation with this. When you have very safety critical systems, that's what the engineers do, because that narrows down the possibilities of what the system can do, and you're sure the system is safe. So that's the, let's say, the easy ones. The other ones are the ones based on continuous system. That means the sensors are measuring something which is not binary. It's not 1 or 0. It's something like the temperature, the speed, the pressure, something like that. And what they do with that information is that they do some differential equations to, for example, do some cruise controls or keep the plane at the same altitude and this kind of stuff. So you have these kind of systems around you all the time, but it's quite actually tricky to do. But the principle is the same. You have a clock and you measure something, and in the input you compute your equations, and then in the end you have an output that will fulfill the goal. Now, if you take the binary systems we talked about it before, and if you wanted to test such a system, you just have to generate a set of inputs and measure the outputs, like that's what you do in testing, but you have to do it for each tick clock. So that means you have a huge amount of information, because the number of times you read the sensors is sometimes 100 times per second. So you end up with like a list of information that are very often the same value, the same data, repeated again and again and again and again. And then at some point one of the inputs will change, and then the output will change. And that's where the idea came from. And then we thought, is these useful, because they're all the same? They're always all the same. Even the history is the same. So it repeats the same inputs so many times. But what we really care about is this event here, when the input 2 goes to 1. That's an event. Then we thought, could we apply event-based testing on some binary clock-based system? Yes? So now if we have a quick look at what an event-based system is, and I'll use as an example an SDL representation of an SDL model, which is used often for telecommunication systems. Basically, the system is based on messages, and you exchange messages with another entity. And the messages can happen anytime. But the messages come with a lot of information, so they're not binary or stuff. They come with a lot of data. That's why you use them in telecommunication. You exchange data a lot, and that abstraction level is quite high compared to what we saw before with a Boolean sensor. This is quite high level representation, and the fact that when you have different processes running in parallel, that generates a lot of possible combinations. Because here, since you don't have a clock-based system, events can occur anytime. So the sequence of events matters, but the possible combinations of events is huge, especially if you take into consideration the value of the parameters coming with the messages. So that's why I wrote this. It generates complexity, and it's hard to verify. And that's why people use the clock-based systems at the lower level or safety critical systems. Okay? But you will see that because of its abstraction, it's much easier to manipulate than a clock-based system. Now, if we want to test a model-driven system, well, you would use also an event-driven notation like TTC3, where you send a message to your SUT and you check the answer, and you decide if you are correct or not. You can have this graphical MSC representation here, where you send M1 to your system. Is it M2? Okay, it's M4. It's not okay. Okay, pretty simple, except that usually you have a huge number of parameters coming with the message. You have a lot of control of the parameters before you can decide if you pass or fail. Still, it's pretty simple notation for a test, isn't it? It's pretty synthetic, and if you want to communicate with people which are not technical, it might be helpful. So if we try to apply this to a clock-based system, as I said before, you would simply look at an input, a logical input like a Boolean. If it stays in the same value, you do nothing. And when it changes its value, then you generate an event. And that's all you care about, really, okay? Because that means something happened. So if you look at a train, for example, maybe the train stops or the door opens or something like that. What you care about is the fact that the train stops. Now, how long it took to get there doesn't really matter in your system here. So if you look at one input, one event, looks pretty simple, and it is actually pretty simple. You can translate all the logical inputs with an event-driven message in the system. Now, if we take something which is not binary, then it's a bit more tricky. Then you have to define a threshold, and you say when the speed, for example, it's the speed of a car, for example, reaches 75, then you generate an event. Okay? But then you don't look at how fast you reach the speed and how far you go away from the peak. Right? It's like quite basic. So let's keep it basic and see if we can apply that. But that's the basic idea, is to define a threshold and generate an event when the threshold is reached. In a system, if you look at the high-level requirements, they are very often event-based. They are not clock-based, or like Boolean equations are quite usually event-based. As I said before, people writing the requirements are not often technical, so they might use natural language. So you have to have let's say, a simple representation of what they're trying to do. Now, we more and more use model-based requirements. So it's coming to sort of transform the natural language to some more formal graphical representation. But when you do conformance testing, you are close to the requirements. So that means you are probably event-driven, you're not clock-based, even though the implementation might be clock-based. So that's a trick you have to solve. And that's why it's interesting to link the requirements, the model-based approach, which is event-based, to some clock-based approach. And that's what we are promoting here. Also, we are looking now at systems that combine event-driven parts and clock-based parts. I talked about the cruise control, for example, in a car. Cruise control is clock-based to adapt and keep the speed of the car the same value, but the user of the car, the driver, is not clock-based. He pushes the button, on, off, increase the speed, increase the speed, decrease the speed, sorry. So he's event-driven. And more and more systems now combine these two approaches. You have to deal with something which is event-based and something which is clock-based, especially with all the IoT and all these communicating systems. So to do so, you have in your system to combine two parts. And one of the ways to do so is to use FMI, which stands for Functional Markup Interface. And that's a way to combine different models or different approach together and have them to communicate. So it's coming from the clock-based world, so it's really the interface is really clock-based, but still, I mean, you can make a bridge, as I said before, and connect an event-based to a clock-based, and that's what we try to do on these use cases. So in practice, what you have to do is that you have to read the interface between the event-driven and the clock-based systems, and you have to decide what will create the events, what will be the name of the events created, what will be the value of the threshold, and how it will translate into the other system. So that's the interface between the two parts. And then, well, hopefully, you can write your test with an event-driven notation, such as TTCM3. So you get your requirements and translate them into TTCM3, and hopefully, with the FMI, you'll be able to, in the end, test your clock-based system, or part of the system, not the whole system. Okay? So if I take, what we try to do is, okay, we have these use cases, so that it's not easy to show. So we actually took an example of a cruise control, and I don't know if you're familiar with SCADE, which is a cloud-based modeling tool. So we have an example of a cruise control. So we took that, and we with the FMI we made an interface, and we tested the cruise control coming from SCADE, which is clock-based, with an event-based notation, which is TTCM3. So I'm putting here the notation in MSC of the test. So it's fairly simple. You'll see. When you start the system, it should be off by default. So it should tell you it's off, the cruise control in the car. And here, when you drive, you press the accelerator, and when you see the speed is above 30, then you switch on the cruise control, and you release the accelerator, and then the cruise control should be on. Okay? So that's you can see this is very close to a requirements, a high-level requirements. You don't care about how it will be implemented, but it's quite readable for someone writing the requirements. Yes? So Okay, I'll come back to that. It's like a small demo to show you what it does. It's a bit long because it's an animated GIF, which is quite slow. And so if you want to take questions in the meantime, I'll get to my conclusion. That what we believe is that event-driven testing is highly suited for a lot of things. And because it's readable, it's closer to the requirements. And as explained, you can test any type of system. I mean, it doesn't prevent to make unit testing, okay, on a control law or differential equation. You will need to do that in any case, but from a functional point of view, it's not very interesting for the people writing the requirements. But it's something you have to do anyway. So I'll put on the demonstration where you have these 3 test cases that will run on this cruise control, and in the implementation here, you have actually you see a lot of messages because the information you read each clock tick is translated to a message. We have left everything so that you can see all the information going, but the relevant information is the one that is written in the test case we saw before. So it's just a few messages exchanged, and actually you can see the huge number of information exchanged between the SUT the test case, while in reality what you're testing is only a few exchanges. Okay, I'm done. I leave it running.